Whenever you look at a huge bridge or even just a simple wooden beam in a building, you have to wonder, how does it just stay there, right? On the outside, it looks completely still, totally at peace. But what's really happening inside? Well, that's a different story. Inside, there's this constant, invisible battle going on just to keep the whole thing from collapsing. So let's dive into that hidden world.
See, what we notice is the macro view, right? A load pushes down and the supports push back up. Seems simple enough. But the micro view, what's happening inside the material itself, that's where the real drama is. The beam is literally fighting back against being bent, twisted, and torn apart. This whole explainer, it's the story of that invisible internal fight.
To really get how a simple shelf holds up a huge stack of books, you have to imagine what's happening deep down inside the material itself.
Think about it. When you put a heavy box on a shelf, the wood doesn't just give up and snap, right? It fights back. There are these internal forces that wake up inside the material to push back against the load and keep everything in balance. But what are they exactly?
Okay, so if we could just make an imaginary slice through a loaded beam and peek inside, all the super complex stresses and strains going on in there can really be boiled down to two main things, something called a shear force and something called a bending moment. And let me tell you, understanding these two is the key to everything.
So first up is shear force. The easiest way to think about this is as a vertical cutting force. It's the force that's trying to make one part of the beam literally slide past the part right next to it, almost like you're trying to shear it in half.
And then we have the bending moment. Now, this is the internal force that causes the beam to, actually bend and curve. It's a turning effect that's trying to rotate one part of the beam. But where does that turning actually come from?
Well, this is how. When a beam sags downwards, think about what's happening. The little fibers at the very top are getting squished together. We call that compression. And at the exact same time, the fibers at the very bottom are getting stretched apart, and that's tension. It's this internal push and pull, this tug of war between compression on top and tension on the bottom, that creates the turning effect we call the bending moment.
But hold on. Okay, so before we can go inside the beam, we first need to get a handle on the external forces that are duking it out on the surface. We have to meet the attackers, that's the loads trying to break the beam, and the defenders, the supports that are holding everything together.
So on the defensive side, we've got our supports. Think of a roller support. It can only push back vertically. That's it. Then there's a pin support, which can push back both up and down and side to side. But the ultimate defender, that's the fixed support. It resists vertical forces, horizontal forces, and any attempt to rotate it. Each one provides a very specific kind of pushback.
And on the attack, you have the loads. A point load, that's like a person standing on one foot. All the force is concentrated in one single spot. A uniformly distributed load, or a UDL, you can think of that like the weight of a heavy concrete slab spread out perfectly evenly. And a uniformly varying load, or a UVL, imagine the pressure of water against a dam. It's weak at the top and gets incredibly strong at the bottom.
Okay, so before we can peek inside the beam, we first have to figure out the external balance of power. We need to know exactly how hard those supports are pushing back against the loads. This whole process is called calculating the support reactions.
We saw this with two basic laws of physics, the laws of equilibrium. First, the sum of all the up and down forces has to be zero. Pretty simple, right? Everything pushing down has to be perfectly balanced by everything pushing up. Second, the sum of all the rotational forces, or moments, also has to be zero. This just makes sure the beam isn't, spinning around. With just those two rules, we can figure out the unknown forces at the supports.
So let's make this real. Let's say we've got a 5-meter-long beam. We put an 80 kilonewton load on it, but it's a little off-center. It's 2 meters from the left support. So how does the beam split up that work between the two supports?
Using some handy formulas that come from those equilibrium equations, we can solve this pretty quick. Think of it like a seesaw. The support that's closer to the heavy load has to do more of the work, right? So the reaction at support A is the load, 80, times the distance to the other support, which is 3. Then divide all that by the total length, 5, and that gives us 48 kilonewtons. For support B, we do the same. The load, 80, times its opposite distance, 2, divided by 5, which is 32 kilonewtons. And let's just do a quick check. 48 plus 32. Yep, that equals 80. A perfect balance.
Okay, now that we've got the external forces nailed down, we can start mapping the internal ones. But to do that, we all need to be speaking the same language. We need a consistent sign convention so every engineer everywhere reads the map exactly the same way.
Luckily, the conventions are actually pretty simple. For shear force, we just say it's positive if the forces are trying to push the left side of an imaginary cut up. But for bending moment, it's even easier. If the beam is sagging into a U shape, like a smile, the moment is positive. If it's arching up or hogging into an upside-down U, like a frown, it's negative. Simple as that. Smiling is positive, frowning is negative.
All right, now this is where things get really, really cool. These diagrams we're about to draw, they aren't just random pictures. They are mathematically connected in this really deep and powerful way. There's a secret relationship between the load, the shear, and the moment, and it's all described by calculus.
So here's the big secret. The value you see on the shear force diagram tells you the exact slope of the bending moment diagram at that very same spot. So if your shear force is a big positive number, your bending moment diagram is going to be shooting upwards really steeply. If the shear is 0, guess what? The moment diagram is perfectly flat. They are totally, completely linked.
And that relationship works the other way too, which is just awesome. The total change in bending moment from one point to another is just the area under the shear force diagram between those 2 points. That's it. This amazing little geometric trick is what lets us draw the bending moment diagram super fast without a ton of crazy calculations. This relationship creates this really predictable, kind of beautiful pattern. Just look at this table. Where there's no distributed load, the shear is a flat, constant line, and the moment is a straight, sloped line. Now add a constant load, and the shear becomes a sloped line, and the moment turns into a parabola. Add a linear load, and the pattern just keeps on going. Every step up in the load's complexity adds another degree to the diagram's shape. It's fantastic.
So, we've got the theory, we've got the reactions, we've got the sign conventions, and we know the secret relationship. It is time for the big payoff. Let's take all of these pieces and finally draw the diagrams for our example problem.
Remember this beam, our 5-meter-long buddy with an 80 kilonewton load 2 meters in? And we already did the hard part. We figured out the left support pushes up with 48 kilonewtons and the right support pushes up with 32. Now we're ready to go.
Okay, let's draw the shear force diagram. You always start at 0 on the far left. The first thing we hit is that reaction A, so we jump straight up to positive 48. Then we just cruise across the beam. Since there's no other load in that first section, the shear just stays flat, constant at 48. Then, wham! We hit that 80 kilonewton load pushing down, so we drop straight down. 48 minus 80 takes us all the way to negative 32. We cruise across again at a constant negative 32 until we hit the very end, where reaction B pushes us up by 32, bringing us perfectly back to 0. Beautiful.
Now, for the bending moment diagram, we use our awesome calculus trick. We find the area of our shear diagram. So that first section is just a rectangle, right? Its height is 48 kilonewtons, and its width is 2 meters. So the area is just 48 times 2, which gives us 96 kilonewton meters.
So what does that number, 96, actually mean? Well, that area represents the total change in the bending moment over those first 2 meters. We start at 0, so our diagram goes up in a straight line to a peak value of 96, right underneath the load. And that is the single most important number on this entire diagram. It's the point of maximum internal stress. It's where the internal fight is at its absolute fiercest, and it's the first place an engineer would look to see if the beam is actually strong enough.
So you see, these diagrams are so much more than just a couple of graphs. They are literally a blueprint of that internal fight. They show us, with perfect clarity, exactly where the beam is being strained the most, where it's getting sheared, and where it's being bent to its limit.
Really, what is the point of drawing these diagrams and learning these relationships? Well, it all comes down to one absolutely crucial mission: finding the single weakest point in the entire beam.
This is the fundamental question for any structural engineer. Failure happens where the stress is highest. And for most beams, the highest stress happens wherever the bending moment is at its absolute maximum. Our diagrams are about to point us directly to that spot. And here it is. This is the big reveal, the connection that ties it all together. Remember our calculus rule? The slope of the moment diagram is equal to the shear force? Well, think back to math class. When is a curve at its peak? It's when its slope is 0, right? This means the exact point where our shear force diagram crosses the 0 line is the exact point where our bending moment is at its absolute maximum. That's the critical point we've been searching for.
Think about a diving board or a balcony again, a classic cantilevered beam. Where does it feel like it's going to snap? Right where it connects to the wall, of course. That fixed support is where the internal bending moment is fighting its absolute hardest to keep the beam from breaking off. For cantilever, that's almost always its critical point.
So, now that you can see exactly where the bending moment is highest, you can start to think like an engineer. You can add more material right where it's needed, or maybe even take some away where it's not, to create a design that's both incredibly strong and efficient. And that is the true power of being able to see these hidden forces.